Welcome to G Fun Facts Online. Imagine having a superpower. Not flight, not invisibility, but the power to see through clouds, through the darkest night, even through the thick smoke of a wildfire. Imagine being able to feel the ground shift by mere centimeters from hundreds of miles away. This isn't science fiction. It's the reality of a technology called Synthetic Aperture Radar, or NISAR, and it has completely changed how we see our world. High above us, a fleet of satellites is constantly reaching out, not with cameras, but with radar pulses, to map the very heartbeat of our planet. Today, we're going to uncover how this incredible technology works, from its secret military origins to its vital role in safeguarding our future. It's the story of how we built a virtual antenna in space, thousands of meters long, to unlock a new dimension of sight. So how did we get here? The story starts not in a space agency, but during the Cold War. In 1951, a mathematician named Carl A. Wiley was working on a problem for the US military. They needed a spy plane that could take detailed pictures anytime, anywhere, regardless of weather. Optical cameras were useless against clouds or at night. Radar was the obvious choice since its microwave signals punch right through atmospheric haze. But there was a huge problem. To get a sharp, detailed image from a distance, a radar antenna needs to be enormous. To get meter-level detail from a spy plane, you'd need an antenna hundreds of meters long, far too big and heavy to fly. This is where Wiley had his stroke of genius. He realized you don't need to carry a giant physical antenna. Instead, you can use the motion of the plane itself to synthesize one. The idea was to have a small antenna on the plane continuously sending out radar pulses and recording the echoes as it flew along. Later, a computer could take all those individual snapshots, collected from slightly different positions, and stitch them together into a single, high-resolution image, as if it were taken by one massive, virtual antenna. This concept, initially shrouded in military secrecy, was a game-changer. For decades, SAR was a classified tool for reconnaissance. Its potential for science, however, was too great to ignore. The turning point came in 1978 with the launch of NASA's CSAT satellite. This was the first time SAR was used for civilian Earth observation. Though it only operated for about 100 days before a power failure, CSAT was a spectacular success. It proved that from orbit, SAR could monitor oceans, track sea ice, and map landforms with incredible precision. The secret was out, and a new era of understanding our planet had begun. So let's get into the nitty-gritty. How does SAR actually build this virtual antenna in the sky? First, remember that SAR is an active system. Unlike a regular camera that just passively collects sunlight, SAR provides its own light source by transmitting pulses of microwave energy. This is why it can work day or night. The real magic, though, is in solving that resolution problem. As a SAR satellite orbits Earth, its small physical antenna sends out a beam of radar pulses that illuminates a patch of ground. As the satellite moves forward, it continuously pings a single point on the ground from many different angles. For each pulse, it records the echo that bounces back, but it doesn't just record the echo's brightness, it records its phase. This is crucial. The key to combining all these echoes is the Doppler effect, the same principle that makes an ambulance siren sound higher as it approaches you and lower as it moves away. As the satellite approaches a target on the ground, the frequency of the returning radar waves is shifted slightly higher. As it flies past and moves away, the frequency shifts lower. By precisely analyzing these tiny frequency shifts from all the echoes collected as the satellite flies a certain distance, a computer can mathematically reconstruct the signal as if it came from a single, gigantic antenna. The length of this synthetic antenna is the distance the satellite traveled while that point was in its beam. A satellite with a physical antenna of just a few meters can achieve the resolving power of an antenna that's hundreds or even thousands of meters long. It's an incredible feat of physics and computation. Once we have the image, we have to learn how to read it. A SAR image isn't a photograph, it's a map of microwave reflectivity. The brightness of each pixel tells you how much radar energy scattered back to the satellite from that spot. Several things determine this brightness. First is surface roughness. A very smooth surface, like a calm lake or an airport runway, acts like a mirror. It reflects the radar pulse away from the satellite, so these areas appear black in the image. A rough surface, like a forest canopy or a field of crops, scatters the energy in all directions, and some of it bounces back to the satellite, making these areas appear bright. The second factor is geometry. Because SAR looks off to the side, slopes facing the radar reflect a lot of energy and appear very bright, while slopes facing away are in a radar shadow and appear dark. This is actually useful for creating detailed 3D topographic maps. But one of the most interesting features, especially in cities, is something called double bounce. When a radar pulse hits the vertical wall of a building, it bounces off the wall, down to the flat street, and then reflects off the street directly back to the satellite. This double reflection acts like a corner reflector, focusing a huge amount of energy back to the sensor. This is why cities and man-made structures often show up as collections of intensely bright points in a SAR image. Not all SAR is the same, however. The specific microwave frequency, or wavelength, the system uses determines what it's best at seeing. Think of it like having different kinds of vision. X-band SAR uses a short wavelength, around 3 centimeters. It's extremely sensitive to small details and surface textures, making it great for high-resolution mapping and identifying objects like cars or ships. However, its short waves get scattered by things like leaves, so it can't see through a dense forest canopy. On the other end is L-band SAR, with a much longer wavelength of about 24 centimeters. These longer waves can penetrate deeper into vegetation, right through the canopy to see the forest floor, and even into the top layers of soil. This makes L-band invaluable for monitoring deforestation, measuring the amount of biomass in a forest, and assessing soil moisture. In the middle, you have C-band, with a wavelength around 6 centimeters. It's a versatile jack-of-all-trades, balancing detail with some penetration capability. It's widely used for monitoring sea ice, tracking oil spills, and general land surface changes. But perhaps the most mind-blowing application of SAR is a technique called interferometry, or NISAR for short. This is where SAR's superpower truly reveals itself. NISAR works by taking 2 or more SAR images of the exact same area at different times. By comparing the phase of the radar waves from each image, scientists can detect tiny, almost imperceptible movements of the ground. We're talking about precision down to the centimeter or even millimeter level from space. The applications are astounding. Before a volcano erupts, the ground above the magma chamber often swells upwards. NISAR can detect this subtle breathing of the volcano, providing a critical early warning. After an earthquake, NISAR can create a detailed map showing exactly how the ground deformed, revealing which parts of a fault line slipped. It can monitor the slow, gradual sinking of entire cities due to groundwater extraction, or even detect the imperceptible sag of a bridge under strain. In the year 2000, the Space Shuttle Radar Topography mission used NISAR to create the first-ever high-resolution, near-global 3D map of the Earth, a dataset that is still fundamental to countless scientific and commercial applications today. This ability to see day or night, through any weather, and to measure tiny changes over time has made SAR an indispensable tool across dozens of fields. In disaster management, when a hurricane makes landfall, SAR can see through the storm clouds to map the extent of the flooding. After an earthquake, it can assess building damage. During wildfires, it can peer through the smoke to map the fire's perimeter. Environmentally, SAR is a planetary watchdog. It's used to detect illegal deforestation in remote rainforests and to spot oil spills on the ocean, because the oil smooths the water's surface, creating a telltale dark patch in the SAR image. For agriculture, it monitors soil moisture to help farmers optimize irrigation and tracks crop growth to help forecast food supplies. And of course, its original purpose in defense and security remains vital for surveillance and monitoring. The future of SAR is brighter and more active than ever. For a long time, this technology was the exclusive domain of large government space agencies. But now, a revolution is happening. A new generation of commercial companies is launching entire constellations of smaller, more agile SAR satellites. This is dramatically increasing how often any given spot on Earth can be imaged, from weeks or months to days or even hours. And it's making the data more affordable and accessible to everyone. And on the horizon is the NASA-ISRO Synthetic Aperture Radar mission, or NISAR. This joint project between the US and India will be a game-changer. NISAR will systematically scan nearly all of Earth's land and ice every 12 days, using two different radar frequencies, L-band and S-band, to create an unprecedented, continuous time-lapse of our planet in motion. It will capture everything from the slow creep of tectonic plates to the rapid devastation of a landslide. Synthetic Aperture Radar began as a secret tool of espionage, born from a clever solution to a physical impossibility. Today, it has evolved into one of our most powerful instruments for global understanding. It looks past what our eyes can see, peering through the chaos of clouds and darkness to measure the subtle, rhythmic pulse of our living planet. The silent dance of these satellites in orbit isn't just mapping the Earth. It's charting its heartbeat, giving us the knowledge we desperately need to navigate the future on this dynamic and ever-changing world. Thanks for tuning in to Fun Facts Online.